Thanks very much for giving up your lunchtime to me. And thanks to Alex for the introduction and inviting me to talk. I'm a fourth year PhD student, but I promise this isn't going to be all technical and sort of end of PhD angsty. I'm hopefully going to give you a very general introduction to why we care about sulfur and the climate and how important sulfur is in our understanding of climate over time. So in order to do that, I'm going to give you three main case studies for where sulfur has really impacted our understanding of the Earth's climate on a large scale, and then talk really quickly about how we analyse that sulfur, and that then, if there's time and you're not all asleep, then show you a little bit of the data that I've been working on to kind of fit into this puzzle. So, first important question is, why do we care about the sulfur cycle at all? And really, the primary answer is because of carbon. So carbon is really, really important to us because variations in the carbon cycle affect how much CO2 is in the atmosphere, which is intimately linked to the temperature of the Earth's surface. And so we care about that. I mean, all life cares about that to a first order. And one of the primary mechanisms by which carbon is broken down from organic matter into carbon dioxide in the absence of oxygen is the reduction of sulfate to sulfide during bacterial sulfate reduction. And so the presence of sulfate in places like ocean sediments actually ultimately affects how much organic carbon is remineralized and added to the atmosphere as CO2 versus how much is buried as organic carbon and locked away in the rock record. Now, on longer timescales, sulfur and the sulfur cycle actually affect the net oxygenation of the Earth's surface. This is because what happens is sulfur is dissolved either as reduced sulfides, sulfates, or just elemental sulfur on the Earth's surface, on the continent, and washed into the ocean as sulfate, and then reduced by bacteria. That reduction to sulfide is normally in high ion conditions. So the sulfide and the ion react to form pyrite, which is solid and locked away in the Earth sediment. So we've taken something oxidized as SO4 and then locked it away as H2S. So we've left a net oxygenation of the Earth's surface. And over long timescales, this can actually act to balance the oxygenation of the Earth's surface. Another really important thing about sulfur is that all these different processes have a different partitioning of isotopes. So for those of you for whom isotopes is a rather like a concept that you haven't thought about recently, isotopes are two atoms of the same element which have different masses, are different isotopes. And because they have different masses, they behave differently under different biological and physical processes. And so under lots of these different processes, particularly bacterial sulfate reduction, the reduction of sulfate to sulfide, there's a very large and distinct partitioning, which we call fractionation. And then that means that if we go to a rock and we look at sulfur, then the ratio of the different isotopes in that sulfur will tell us something about how that sulfur got into that rock. And a quick note on numbers, where we don't measure the raw ratio of sulfur, mostly because they're rather unwieldy numbers to use. So we measure them relative to an internationally calibrated standard. So all the numbers are essentially between -17 and +30. It's just an easier scale, but you'll see delta notation for the rest of the talk. So one of the first things that geologists really care about, or climatologists, is how the Earth's climate looks like it does today. How have we got to this point from a molten ball of slowly cooling rock? And that goes from how did we get out of this last ice age, right the way back to 4.5 billion years ago, and how did we get to oxygen in the atmosphere from this boiling ball of rock. So the Earth solidified about 4.5 billion years ago, and then we have really early evidence of water. So liquid water was on the Earth 4.4 billion years ago. And the temperature conditions, in order to allow liquid water to survive on the Earth, was such that we must have had a methane and CO2 rich atmosphere in order to keep the Earth warm enough for liquid water to live. So But we have a problem in that we can't just produce atmospheric oxygen, free oxygen. The best way of producing oxygen is through photosynthesis. So these are cyanobacteria. They're the most primitive photosynthesizers that we know of. And we have putative evidence of them as far back as 3.5 billion years ago, but more solid evidence, more robust evidence at 2.7 billion years ago. And these things are photosynthesizing, producing oxygen, but that oxygen is being produced into an atmosphere that is very reactive with respect to oxygen. So as soon as the oxygen is produced, it's going to react with methane to form CO2 and hydrogen to form water. So there's a huge gap between the first evidence for these things and the first evidence for free oxygen in the atmosphere. And this is where sulfur comes in, because sulfur, it turns out, is really sensitive to very low levels of atmospheric oxygen. And this is because in the earlier, so SO2 comes out of volcanoes. That's principally the way we end up with SO2 in the atmosphere, before humans started burning lots of things. So SO2 comes out of the volcanoes, and in the presence of UV light, it will split, it will partition into different isotopes. As soon as there's about 1% of today's atmospheric oxygen in the free oxygen in the atmosphere, then it will start to react to form ozone. And as soon as we've developed an ozone layer, then that is sufficient to shield the SO2, or the majority of terrestrial SO2, from UV rays, and so it doesn't photolize anymore. So you can see this is a record of the partitioning of sulfur isotopes over time. So it goes from 4 billion years ago to today. And you can see that there's a really large partitioning, there's a really large variation in the isotopes up to 2.5 billion years ago. And then suddenly it's really, really consistent and there's no variation at all. So this fits in. We know that from here we've got 1% present atmospheric oxygen. And then we can start thinking about having enough photosynthesizers on the planet that we're actually maintaining an oxygenated atmosphere from then for the rest of geological history to date. There's another way that sulfur tells us about this oxygenation of the atmosphere. So this plot, the middle panel on the left-hand side is the plot I've just shown you, and I want you to ignore the bottom panel. The top panel, the top line on that is what we think sulfate, SO4, in the ocean was doing over time. Now, all of the dots are the spread of sulfides. So I was telling you that SO4 is reduced to H2S. Sulfate is reduced to sulfide by bacteria. And so the sulfide that we measure is bacterially produced sulfide that's being preserved. And you can see that up to the start of atmospheric oxygen, that top line and all of the dots are very similar. There's actually very little difference. Now, I said that bacteria will partition isotopes very, very well when it wants to reduce sulfate to sulfide. But if there's very little sulfate around, then it will just take all the sulfate it can. And so under those conditions, there will be no partitioning because it will have quantitatively reduced all the sulfate. So this gives us evidence for very, very little sulfate, very little SO4 existing on the Earth's surface. Now, under a very poorly oxygenated Earth, that's what you would expect, because there's not really enough oxygen for SO4 to exist happily. Every time we reduce it to H2S today, any free oxygen that the H2S meets will oxidize it. But if there's not very much oxygen around, then H2S is relatively stable. So you can see, fitting very nicely with what I've described already, that as soon as we reach a rise in atmospheric oxygen, the spread of dots versus the line get a lot larger. So we can see that suddenly there's enough sulfate, because there's enough oxygen transporting sulfur into the ocean, keeping it as sulfate, in order for bacteria to partition away merrily. But the next thing that you can observe is that up to about 600 million years ago, so 0.6 billion years, the spread is about half of what we see after that. So there's a very different condition in the Earth for that huge length of time, 2 billion years, and then suddenly we get a much larger amount of fractionation. So So if we're thinking about a simple model where this is all dependent on sulfate concentrations, then something fundamental happens at 600 million years ago, which increases the sulfate concentration of the ocean. And this is a really, this plot is just showing it much more clearly because it's the average of the moving average of the global spread rather than all of the data. So this gave rise to one of the most important theories that we have about the early ocean. So the initial canonical story of the ocean was that the atmosphere was gradually accumulating oxygen, but there was no oxygen in the ocean, and then over time enough built up in the atmosphere that we oxygenated the ocean. And at this stage we have the idea, we have evidence for lots of iron in the ocean up to this point, so that fits quite nicely because we don't have very much iron in the ocean when there's oxygen, so we're thinking, well, here we've got, then suddenly everything's oxygenated. But we hit a problem with that because we know that from at least 2.7 billion years ago we have life. But we don't see any higher form eukaryotes and any actual macroscopic multicellular organisms until much later. But we've got allegedly an oxygenated ocean that should be functioning, if not like today, then similarly enough for evolution to start kickstarting. So what has happened? And this low concentration of sulfate in the ocean is the thing that first gave us the clue to this. So actually now we think the ocean is much more like this. So instead of just being iron-rich, oxygen-poor, and then boom, oxic, we go to a very sulfidic. So lots of H2S, lots of low SO2. So there's not very much SO2 for this bacteria to split, like we saw in that plot earlier on. And this ocean is a much, much more toxic ocean to higher eukaryotes and higher forms of life because sulfide is incredibly toxic, except for some species of archaea and bacteria. So this suddenly fits a lot more nicely into our picture of how the world works. So the third example I'm going to give you is one from the largest mass extinction that's on Earth's history. This is the Permo-Triassic mass extinction, which is 250 million years ago, so we're moving slowly towards the present. And there's always a lot of theories for a mass extinction. The most popular is always a meteoroid impact, without fail. But in this case, if you look at the sulfur isotopes, then that gives a much more, well, a very different and much smellier idea of what was actually going on. So this is from a rock succession in China, and you can see there are lots of different biomarkers, like organic compounds that are telling us about microbial metabolisms and things, but I want you to look at this plot. So this is the sulfur isotopes in sulfates in the rock. And you can see that at the extinction horizon, they suddenly go crazy. They get really, really high and then really, really low. And the best way to explain this is that there's a huge build-up of hydrogen sulfide, this incredibly toxic, very soluble molecule in bottom water of the ocean. And then a mass overturning event leads to a huge belch of H2S into the surface ocean. Most things at the time are photosynthesizing or living on photosynthesized in the ocean, not that much lives on the land surface, and this will be enough to really wipe out the whole of the ecological system. And it looks like, you can model this, and it looks like actually there are repeated belches of H2S based on the way we think the ocean circulation worked at the time. And so it's quite a potent and really stinky kill mechanism for this, the most severe mass extinction we've ever seen. So we know quite a lot about sulfur from all of these different, looking at all these different events. But the problem with all of them is that we don't have that many rocks from that long ago. And the ones that we do have been really overprinted. So they've either been like squashed or loads of really acidic fluids washed through them. And so there's a high potential that we've reset our original signal. And the different proxies that we use, the different rocks that we do use, rocks and minerals that we do use to understand sulfur, all have a variety of problems. So the most primitive one, or the first one we started with, was pyrite. So I've talked about the formation of pyrite already and how the isotopes of that are important. But as I told you about this story, if we didn't know what this top line was, which is what we think seawater sulfate was doing, then the bottom line doesn't really make any sense, because it's the difference between the two that tells us that there was enough sulfate for bugs to partition isotopes or not. So then if we think about how we can get this top line, we have two proxies that are normally used. The first is gypsum. So evaporites form on the edges of marine basins that are evaporating very quickly, and the sulfate goes into calcium sulfate, which then is preserved and we can go and look at. And we can create records of it like this. So now time changes where it's going all the time. Time is now coming down, so present day is up there. And so this is for the sulfur, and this is for the oxygen in the sulfate, the isotope ratio. So we have a really nice curve, but actually there aren't that many time periods when we have very well preserved gypsum, because it's formed under intensely hot evaporative conditions. I mean, we're not forming very much of it today, except in very extreme environments that aren't representative of the whole Earth. So while this data looks quite nice, it's actually lots and lots of gaps, and the error bars haven't come up very well, but they're like this. So we do have a problem with that. So there's a second proxy we can use, which is marine barite. Marine barite forms in the open ocean. So barium reacts with sulfate, it falls to the seafloor, and then it's preserved there. So that's brilliant, because we can just go to the sediment, take it, look at it, and it tells us about marine barite. And we can get a really nice record. So this is much, much more high resolution of the last 130 million years. And so again, this is sulfur, and this is oxygen. And barite would be wonderful, but the problem with that proxy is that the sediments that we need to extract it from only go back 130 million years. So beyond that, we're stuck. So there's a new and very important proxy that we're working on developing at the moment, and that's carbonate-associated sulfate. So when carbonates form, calcite, aragonite, limestone, dolomite, they incorporate the sulfate of the fluid that's around them. This is a very simple density functional theory model of such a system. So this is a calcite lattice, and these are carbonates, and this is the calcium, and you can see the sulfate substituting for a carbonate ion in the lattice, and it fits very nicely. There's only minimal distortion of a few of the carbonates. Very happy there. You can put a lot of sulfate in, and then you can go to your 3 billion-year-old rock, extract the sulfate, and measure it, and it should tell you what the water it was in at the time. I told you. So there are several problems. Well, at the moment, we don't know how quickly that's reset, whether it's easily dissolved out and reprecipitated. So when we look at a 3.5 billion-year-old rock, actually we're looking at the fluid that washed through it 1 billion years ago, or 3 weeks ago, or something. So we don't know how well it preserves. And so this is where my PhD thesis comes in. So what we aimed to look at was how much, we went to sites in the ocean with carbonate that are really well dated. So the ocean sediments go back to 130 million years. We only went back the last 30 million years. And we compared the sulfate from this method with the isotope value that we think we know from the barium sulfate record that I showed you earlier. So this is the ship that we went on. I only went on one of these expeditions, but I have data from lots of them. So this is the spread of data that I'm going to show you. And so this is it, just very concisely. So I want you to look at the top panel first of all. The grey line is the barium sulfate record that I was showing you earlier, just zoomed in on the last 60 million years, in fact. And then the colour over the top is my data for sulfur, and for the bottom is for oxygen of sulfate. So for sulfur, the agreement, statisticians will totally disagree with me, but the agreement for a geologist is actually very good, apart from in these two locations, and that is to do with the environment in which the carbonate is. So this is a highly reducing environment, and this is an environment where there's very rapid recrystallization. But I'll talk about this more in detail if anyone's interested. But the real kicker is that the oxygen record looks nothing like the oxygen record of barium sulfate that we think is like our true oxygen isotopes of the ocean. of sulfate at the time. And these data points are not laboratory artifacts. So they've been done several ways. There are lots of possibilities, like when you produce this data, you have to precipitate a lot of crystals, and you could have included other nitrates in there or something, but they've all been cleaned very, very extensively. And it's just come out in the last year that actually this barium sulfate record is formed in places in the ocean where there's such a high turnover of bacteria that the oxygen in the sulfate is not recording what the actual ocean is recording. And if we zoom in on my record for the last 6 million years, you can see that actually there's quite a good agreement with my record compared to the barite record, apart from this point. And so potentially we've actually highlighted a really big problem with the barium sulfate record that we hadn't yet understood. There's no way of verifying the oxygen isotope record that I've created, but we hope to maybe find another way of doing that at some point soon. So the take-home messages really are that we have a great new proxy and it works for sulfur, and this means we can go higher resolution, further back in time, and also look maybe at spatial resolution across the globe. However, the oxygen isotopes, as yet, we're still investigating. So thank you very much for listening.